All right, so let's pick up where we left off, which is trying to go backwards in time. So we know that the universe is expanding. So if we run the clock backwards, the idea is that yesterday the universe was a little bit smaller, and because it was smaller, since you're compressing things, it was a little bit hotter. And a year ago, it was even smaller and a little bit hotter. And if you go backwards in time enough, the universe shrinks, right? If you run the movie backwards, the universe shrinks and gets hotter and hotter and hotter. And then, I mean, to what end? And then what happens? Well, we just run the clock all the way back and we just see what happens. We run it back until we get to a singular point, and then if you let things run forwards again, it's like a sudden expansion called the Big Bang. There's a couple of different things when you say Big Bang. There's the Big Bang refers to the idea that the universe started in this really hot, dense state and then expanded. And it also refers to the theory, which is composed of many, many parts, talking about how the universe got to the way it is based on the fact that it was hot and dense 14 billion years ago. Okay, so we'll use it in that latter context. All right, so what we're going to do is run the clock backwards to when things were very, very small, very, very dense, very, very hot, and we'll just see. We just let our physics equations go forwards. We just run things through and we just see, do the predictions pan out? And how can we make predictions? Well, we understand things at pretty hot and dense and high temperature regimes. How do we do that? How can we run experiments? We can't, of course, make a Big Bang, but we can make tiny little regions of the universe that have the equivalent temperature and density. Maybe not the density, but the equivalent temperature. We can make those regions in what used to be called atom smashers, right? Colliders. There's several huge ones around the world where you smack particles into each other and then, at incredibly high energies. And then out of that energy, what you get is a shower of particles. So over the last 70, 80 years, we've managed to put together a pretty good idea of what happens if inside regions of the universe that are very, very small and hot and dense. So what we do is we just apply that to the universe as a whole and see if it matches up with what we expect. Okay, so here's where we pick up the story. Just imagine in your head running the universe all the way back, something very much smaller. And at this time, at this early time, the universe is only about a millionth of a second old. We can go even farther than that. But we have a pretty good idea of what happened ever since the universe was about a millionth of a second old on into the future. Why? Because we can do those experiments. We can do little subsets of the universe that are that dense and hot, and then we can see what happens. So we just see if this makes sense. All right. At this temperature, if you run the clock backwards, the important thing is that the temperature of the universe was about, and all these are going to be roughly, about 1 trillion degrees, way, 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 way hotter than the inside of a star. At these temperatures, okay, remember we had something that looked like this. That was Einstein's formula, right? And what we said was that a little bit of mass turns into a lot of energy because you're multiplying it by this c squared. You're multiplying it by this, c being the speed of light, a really large number. And so a little bit of mass can create a whole bunch of energy. That's the idea behind how stars work. Well, in the early universe, it turns out that things went sort of backwards. In the early universe, there was so much energy available, the temperature was so high, that out of this energy, physics equations work this way too. It's an equal sign, can go both ways. So out of a whole bunch of energy, you can create mass. We know that that happens because at the atomic colliders around the world, you slam particles into each other. They completely obliterate each other in a tiny little area of high temperature and high energy. And then out of that, you create particles out of the energy. So you can, if you have mass, you can create energy. And then the regime we're talking about, if you have energy, you can create mass. And so over many, many years, we worked out the principles of what particles, out of a certain amount of energy, what particles could be created. So in the early universe, if the whole universe had this temperature, we had a pretty good idea of what particles could be created. And at this time, what you get are protons and neutrons being created out of the energy. And here's the deal. The neutrons, and this whole time, remember, this is a millionth of a second. And so within another fraction of the second, the universe gets a little bit larger, cools off a little bit. So maybe instead of 1 trillion degrees, maybe it's 100 billion degrees. The exact numbers aren't terribly important for us. But here's what happened. If you look it up in a periodic table or in a book, neutrons are a little bit more massive than protons, a little bit. What that means is it takes more energy to make a neutron than it does to make a proton, because there's more mass there. So as the universe was cooling off, what happens is that the production of neutrons shuts down, because pretty soon you're in a regime where you can only make protons and not make neutrons. So the production of neutrons in the universe stopped, and the universe could only make protons. What that means, and so that went on for a little while until the temperature dropped to such a point when you get to about 1 second old, we have all the protons and neutrons in the universe that we're going to have. But what's happened is you've overproduced protons by that stage because they're a little bit less massive. And the calculations show, when we run this through our models, what the calculations show is that we get roughly 7 protons are produced at the end of this time until the temperature drops so low that you can't make protons anymore. You make 7 protons for every neutron. So you've overproduced protons. Okay, and then you get to a point where the universe is cooled off where you're not making protons and neutrons anymore. That number is sort of locked in. So then the universe is about 1 billion degrees. 10 to the 9th. Which is definitely hot enough for these protons to fuse, right? So what happens in the early universe, and it's dense enough so that this happens. In the early universe, you've got, let's see, what color do I want to make it? How about protons? Protons are going to be red. Neutrons are going to be blue. Oops. I might have to just draw them. Okay, so 3, 4, 5, 6, 7. Okay, there's 7 protons just for kicks. I'm going to draw 7 more. 1, 2, 4, 5, 7. Okay, so there's 14. We've taken just a little scoop out of the universe, and we have 14 protons. And if we have 14 protons, we ought to have, oops, 2 neutrons, right? It's a 7-to-1 ratio. Well, in essence, what happens is, when these things start to fuse, is that you get, what happens is that comes together and forms, remember what that is? That's a deuterium. That's an isotope of hydrogen. And then here's another one. And what happens is that these two things combine together, and you get a helium. So there's fusion going on in the early universe. So you get 2 protons, 2 neutrons together, and you form a little bit of helium. Now, here's the cool thing. After all this stops, because this, remember, the universe is rapidly expanding and cooling off. So this reaction takes place. And then what do you have left over is you have, whatever's left over is 12 protons. So in other words, 12 hydrogens, and you have 1 helium. So the ratio is 12-to-1. Well, guess what? The ratio of 12-to-1 is exactly what we observe everywhere in the universe. When this production shuts down, which actually happens, we get fusion for about 20 minutes. Kind of a cool number. When the universe is 20 minutes old, it's now too cold because it's been expanding. It's too cold for fusion to carry on. So when the universe is 20 minutes old, fusion shuts off, and we're left with this ratio. So we have 12 hydrogens for every helium. And that's a ratio of about 92%, to about 8%, which is exactly what's observed. Look at it by mass. I've got 12 hydrogens, and 1 helium weighs as much as 12 hydrogens about. And so by mass, you might say that 75% of the universe by mass is hydrogen, 25% is helium. And the cool thing is this is exactly what we see. This exactly is in line with observations. And at first, this was a big puzzle, because why would the universe have so much helium in it? You might think, oh, because stars make helium out of hydrogen, right, when they're on the main sequence. But this is way too much. Over the whole, the sun is about this much, 75%, 25%. But over the sun's whole lifetime, it only changes that helium number by about 1%. So what we observe is that throughout the entire universe, all stars have about this ratio, and this is way more than they'll ever produce. It's like they were born with this ratio, right? It's like the universe was seeded with this ratio of 75% to 25%. This is not the result of stars making it. This is a result, apparently, of the universe making helium early on in its history, using some of the hydrogen together to make helium. So this abundance that we see traces all the way back to the Big Bang. Stars, again, can change this over their lifetime. Sure enough, they make helium, and then helium is used to make other things too. So it's not clear that the helium is going to really change all that much, but maybe by 1% or so. But that 25% helium that everything seems to start with, that's called a primordial amount of helium. It comes from the earliest stages of the universe, which is really cool. So that's something that's observed. So that solves one of the puzzles. Why is there so much helium in the universe? Where'd the helium come from? Well, here's where it came from. It came from early times in the Big Bang. Okay, neat. Did it go any farther? What else was made in the early universe? It turns out basically nothing. This was it. Because by the time you get this, remember what has to happen. The next step is that 3 heliums might fuse together to make carbon. And the problem with that is you need something. Now, it was sure enough hot enough to do that, but you have to have the right amount of density, right? There has to be enough, it has to be dense enough for 3 heliums to come together to make a carbon. And in the early universe that was expanding and cooling, the universe is just not dense enough for that to happen. That really didn't happen at all. So in the early universe, which is surprising, because you think, oh, it's so hot that the entire periodic table was made. Turns out, no, this is the bottleneck. This is the bridge that the universe couldn't cross. At the beginning, the universe only made, there was only hydrogen from the protons, and then the universe made helium. And there was a smattering, the calculations show that there's a smattering of other things. There's a little bit of lithium, a little bit of beryllium, a little bit of deuterium left over. So, but basically, it's all hydrogen and helium in the Big Bang. Nothing else. It wasn't dense enough and hot enough then to form carbon. So that had to wait for stars. It had to wait, it turns out, like 400 million years for stars to be born to make carbon. So the early universe was just hydrogen and helium, which is cool. By the way, one way we can test this, because this is what the calculations show, but then you wonder, like, is this real? So one way that we can test this is we can go look at gas clouds that formed early in the history of the universe and haven't made stars since. So these are called primordial gas clouds. They exist in between galaxies. It's just gas that nothing has happened to this gas in 14 billion years since the Big Bang. So the reason that we want to use those gas clouds is because other gas clouds where stars have formed, remember, stars pollute the gas with all these heavy elements that they make. So if you really want to know what the Big Bang was like, go look at gas that comes from the Big Bang that hasn't been sort of polluted by stars yet. So when we look at those gas clouds, what we find, maybe not surprisingly, but amazingly, is we find this exact ratio, 75-25, and we find the exact ratios of all these other trace elements, some of them traced down to 1 part in like 100 million in the case of like beryllium. We find those exact ratios in these clouds, which gives a great deal of support. The fact that all of those independently line up gives a great deal of support to these calculations that we think we understand the early universe really well because the predictions actually bear out. Okay, so the early universe only made hydrogen and helium and just a smattering of other things. And then once the production shut down after 20 minutes, what's left? nothing can happen for a really long time. The universe is very, very hot. It's not hot enough to fuse, but way too hot for stars to form. In order for stars to form, you need to have the universe being fairly cold, because the motions of the molecules have to be pretty slow, because they have to slowly start coalescing into a star. If it's hot and they're thermal motions, if they're really busy because it's a hot gas, it's never going to gravitationally collapse because it's too agitated. So nothing happens in the universe for about, we go on to about 380,000 years. That's kind of a jump forward, right? From a fraction of a second to 1 second, 20 minutes. Now we jump forward because, as far as we're concerned, nothing much happens until 380,000 years in the future, or when the universe is 380,000 years old. And here's the thing we were talking about, where the universe is down to about 3,000 degrees. The whole universe is about 3,000 degrees. It's glowing. The whole universe is glowing, sort of a dull red color. What happens at this temperature is kind of neat. Up till now, the universe is too hot and too dense for atoms to form. I mean, we said hydrogen and helium, but what we mean are just those nuclei, just the protons and neutrons. There have been electrons this whole time, but the electrons are just bouncing around. And any time an electron is captured by a proton, now there's a collision that pops it right back out again. It's too hot. There can't be atoms. Everything is ionized. At 3,000 degrees, there's a neat sort of a phase transition. And by phase transition, I mean that things change over a small degree of temperature. You have big changes, sort of like water. You know, over a couple of degrees, water goes from liquid to solid. So there's this phase transition of the universe that happens at about this temperature, where all of a sudden, once the universe keeps expanding and cooling, now electrons can be captured by protons to form the first hydrogen atoms. So now we have protons with electrons circling them, and you get the first hydrogen atoms and helium atoms. Why is this important? Because it turns out free electrons make sort of a fog. Light can't travel through free electrons like a plasma. So it's a thick, opaque fog. But once they're captured, remember, the only way that light is going to be absorbed by a hydrogen atom if it happens to be in those special frequencies, right? Those special colors that hydrogen can absorb. Otherwise, the light just sails right on through. So at this time, what happens is when you form atoms, the universe is transparent. Before this time, it was a thick fog, and light couldn't really travel from point to point. But as soon as you form hydrogen, the fog clears, and the universe is transparent, and all this radiation is now free to travel. In particular, remember our model of the universe is like a sphere. Here's us. So at early times, all this radiation from early times is just now getting to us. And we can see it because now the universe is transparent. So one question you may have been having is, you know, as we look to galaxies further and further away, we're looking further and further back into time. So how far back can we actually look in time? Can we see all the way back to the Big Bang? And the answer is no, but close. We can see all the way back. As long as the universe is transparent, we can keep looking at things that are farther and farther away. The problem is that the light has been redshifted, right? Because it's been traveling along the universe that's been stretching this whole time. And so this temperature of light is redshifted by the time it gets to us. How much has been redshifted? From this time till now, the universe has expanded by a factor of about 1,000. I think I said like 1,100 last time. So where is that light now? It just gets to us after traveling basically all the way across the universe. And now, after a redshift of 1,000, it's got a temperature of only 3 degrees. And 3 degrees happens to be microwaves. So the light has been redshifted from a dull red color all the way down into the microwave part of the spectrum. This was forecast back in the 50s and 60s when people were starting to work on this. People thought, oh, if we look far enough back in the universe, we might see some microwaves from this era after the Big Bang. And so people started looking for it. But who actually discovered it were technicians from Bell Labs, because they had just launched space satellites to communicate over the oceans. And they noticed whenever they tried to communicate with these satellites, they just happened to be using these microwaves. There was this hiss coming from everywhere in the sky, this interference, the static. And what they figured out finally was what they were listening to, the static coming from everywhere on the sky, was actually the background radiation from the Big Bang. They discovered the leftover heat from the Big Bang. Like you turn your oven on, you cook something, you turn your oven off, but later you put your hand in, you can still feel a little residual heat. This is the residual heat from the Big Bang that's just now getting to us, and it's the microwave radiation in the background, and we call this, guess what? Cosmic microwave background. And when we look at it in detail, this thing to the left, this thing is a whole sky plot. It's supposed to represent the entire sky. What we see is that it's a little bit lumpy. Only a teeny tiny bit. The lumpiness has been really magnified for this image. It's really like the blue areas are supposed to be the cool areas, like here, and then the red areas, red yellow areas are supposed to be the hot areas. Those only differ by about 100,000th of a degree in temperature. So this has been really accentuated. Really, it's just a uniform thick fog of microwaves in the sky. And this was discovered around 1964, something like that. And it's already got this lumpiness. And so when we investigate the cosmic microwave background, we can already see that matter has started to clump together that will later form superclusters and clusters of galaxies. So the universe already at 380,000 years old is already lumpy. It's already starting to form, it's starting to self-gravitate and form these clusters and lumps. But this is a spectacular confirmation of Big Bang Theory. One of the reasons is, first of all, we predicted that it ought to be there, and then you go and find it. And then if you look at it in detail, here's the spectrum. Look at the spectrum of the background radiation. The blue line is a blackbody spectrum at about 3 degrees, just a theoretical one that you could cook up on a computer. And then the red pluses is the actual data. And the actual data fits the blackbody curve exactly. The universe at that time was exactly a blackbody. It's amazing. And it's also cool for what's not there. Look at that plot. This kind of looks like the plots of stars that we dealt with before, but the main difference is, look, what don't you see? If this was if I told you this was a stellar spectrum, you might think that it's probably not, because the things that you don't see, it's not messy, right? There's no spikes. Remember, stellar spectra had these downward pointing absorption lines that had all these spikes. When we look at the microwave background, though, there are no spectral lines, which is kind of amazing. What this means is, of course, what this is really telling you is that this light came from a time when there were no atoms to absorb it, right? This is why it's also a spectacular confirmation of the Big Bang, because we're looking at radiation that hasn't been absorbed. It just floats right through and gets scattered by all the free electrons. There's no spectral lines because there's no atoms yet whenever this radiation is being propagating through the universe. So this microwave background has some really interesting features, and it's kind of ironically because it's the lack of features, right, that make it really interesting. So this was emitted at a time when there were no atoms. So all of these ideas about the Big Bang and the predictions start coming together. Okay, so what happens after this? 380,000 years after this, you actually have to wait about 400 million years. The book talks about this a little bit, for the first stars and galaxies to form, because again, the universe has to cool off enough for the gas to be able to condense. So the universe goes through a period called the Dark Ages for about 400 million years. And then you get stars and you get galaxies, first small galaxies, and then they combine to form bigger galaxies and so on. all the way up to the present day. And then what do we know about the universe in the present day? We'll pick that up in one more short video. It's a cliffhanger. We'll pick that up in one more short video.